the last few lectures we discussed about the basic concepts of propositional logic, where we mentioned few things, some of the important concepts such as what is considered to be validity, satisfiability, logical consequence, etc., in a very superficial manner. In this lecture we will be talking about one of the important decision procedure methods that is employed in the propositional logic. So, that is semantic tableaux method. So, we will talk about semantic tableaux method in little bit in somewhat greater details, and we will be dealing with some examples how to use this particular kind of method. So, then we will make use of this method in solving some of the important puzzles such as knights and knaves puzzles and lady or tiger puzzles. Both the puzzles are constructed by Raymond Smullyan in his famous books. The first book is What is the Name of the Book? The title of the book itself is What is the Name of the Book? And the second one is Lady or Tiger, and some other subtitle is there. So, both books are very interesting to read. There are lots of puzzles involved in it, but we will be solving these puzzles by using semantic tableaux method. So, we might be wondering why we need to use this semantic tableaux method, especially when there are lots of other decision procedure methods such as truth table and some other methods which are available to us. So, truth table is considered to be simple, straightforward, etc., but the problem is that when the number of variables increases, then it is very difficult to monitor the entire truth table. For example, if you have number of variables number of variables exceeds more than 4 or 5, there are, for example, there are 5 propositional variables p, q, r, s, etc., then we have 2 to the power of 5 entries are going to be there in the truth table. So, for checking the validity, how do we check validity with the help of truth table method? It is simple and straightforward. You need to find out a row in which you have true premises and a false conclusion. Suppose if you have a argument like p implies q and not q. So, now you need to inspect a row in which your premises are true, that means p implies q is true, but not q, that is false. So, when you have a true premises and a false conclusion, the argument is considered to be invalid. But the problem there is that it is pretty straightforward, simple, etc., easy to use, but the number of variables increases and things would be very difficult. For example, 2 to the power of 6 entries, for example, it's very difficult to monitor that particular kind of thing. So, semantic tableaux method conducts a kind of direct search for the models. One of the important thing you need to note is that all the open paths of a tree corresponding to satisfiability of conjunctions of formulas which are occurring at the node. So, what essentially you do here is that for checking the validity of a given argument, what you do is you deny the formula and then you try to see whether all the branches closes or not. If all the branches closes, denial of the conclusion, denial of the formula not x is considered to be unsatisfiable because all the branches closes. Then unsatisfiability of not x guarantees us that x is valid, and for satisfiability you need to take a given formula or set of formulas and you construct a tree diagram for these things, and then if any branch is open, that means under that particular kind of interpretation, whatever values that you have in that particular kind of path, that particular thing is considered to be satisfiable. Or two groups of sentences, for example, well formed formulas, you will come to know whether they are consistent or not by listing out one after another and construct a tree diagram and see whether all the branches open or not. At least some of the branches open, and that particular path tells us when a given formula is said to be consistent, under what interpretations a given formula is satisfiable or true. The traditional approach such as constructing a truth table can make 2 to the power of n steps, where n is sufficiently large, then it is difficult for us to monitor the entire truth table. So, it is difficult to handle propositional letters, particularly when n is considered to be large. So, there are few definitions that we need to note before entering into the examples. In a tree diagram, there is something called as path. So, you need to imagine an upside down kind of tree. A tree has a trunk at the base and then you have branches. So after constructing the tree, the idea here is that you need to end up with atomic propositions. So unless until you end up with atomic propositions like p's, q's, r's, etc., you will be constructing, you will be using the semantic tableaux rules again and again to generate these atomic sentences. You will end only when you end up with atomic propositions. So there are a few definitions that we will be using it here. First, a path of a tree is considered to be a complete column of formulas from top to bottom of the tree. So the given well formed formulas are sitting at the node, and then it ends up with a particular kind of atomic formula, and the whole thing is considered to be a path, or it is considered to be a route going from the initial set of well formed formulas from top to bottom till you reach atomic propositions. And when do you say that a path is considered to be finished? When a literal and its negation occurs, a path is said to be finished. There is no way in which you can advance in that particular kind of path. There is already some kind of contradiction. So we have P and you have not P, then obviously you need to close the path. And an open path is a path that has not been ended up with, we usually cross it so that whenever you have a literal and its negation occurs, we close the branch or that path closes. So why you need to close the path? Because inconsistency is treated as some kind of hell, or the problem here is that if you have inconsistent kind of propositions, you can derive anything. Suppose if you have P and not P, you can derive Q, you can even derive not Q also, where Q is considered to be a bit of a kind of strange proposition by simply following the rules of classical logic. So these are some of the definitions that we will be following in the semantic tableaux method. A formula occurs on a path if it is on the path and it is merely a sub formula of some other kind of formula on that particular kind of path, where it is considered to be unchecked. So all these things it will be clear when I talk about some examples. So there are some strategies that we employ in this semantic in using this semantic tableaux method. So we need to ensure that we always use non-branching rules. Non-branching rules means, for example, if you have not of P or Q and you have another formula P or Q, the first thing that you do is you apply, you have to adopt some kind of bit of strategy where when you apply the semantic tableaux rule, it should not lead to a branch. The first formula that you are going to apply on is a non-branching kind of rule that you need to apply before applying the branching rules. For example, P or Q leads to a branch. In the same way, P implies Q leads to not P or Q. So now using this semantic tableaux method, now we can talk about all the things that the truth table does or any other method does. There is another method called resolution refutation method, which is quite popular in the computer science in particular. So all these methods are very important, but depending upon our convenience we use these things. All these things are suggesting the same thing. Depending upon our convenience we will be using these things. So if you want to determine the validity of a given formula x, what you do is you start the negation of the formula and see whether all the branches closes. If all the branches closes, and you will say that not x is unsatisfiable, not x is unsatisfiable guarantees you that x is considered to be valid. If you want to show that two groups of statements are considered to be inconsistent to each other, then you list out all the statements one after another and you start constructing the tree diagram by using the tree rules, and then you will end up with the atomic propositions. If all the if at least some branches open, that tells us that the given group of statements are said to be consistent to each other. For example, if you have P and not P, if you construct a truth table for that one, all the branches closes. A formula is said to be a tautology. As I said in the last class, in classical logic we have three groups of statements. One is contradiction, which is considered to be always false, like 2 plus 2 is equal to 5. On the other hand, we have tautologies, which are always true. It doesn't require any, it is always true, like they are like self-evident truths, axioms, theorems, etc. are all tautologies. And there are some set of other statements which are sometimes true, sometimes false. They are considered to be contingent kind of statements. So you need to note that when we are going to discuss this modal logics, one of the important problems that we will be addressing is how to represent the future contingent sentences. So what kind of value, the truth value that a given future contingent sentence takes. For example, if you say that I will be in my native place on so and so date, so what is going to be the truth value of that particular kind of thing? Classical logic fails to differentiate between something which is actually the case, something which is possibly the case, and something which is necessarily the case. That is the reason why we will be doing modal logic, and before doing modal logic, which is modal logics are considered to be an extension of classical logic. That is why we are doing classical logic in somewhat a kind of we are doing some kind of crash course on classical logic, where we will be highlighting on some of the important things. You should note that this is not considered to be detailed kind of study of classical logic. So these are some of the things that we will be observing it in the case of semantic tableaux method. A completed semantic tableaux for a given formula A, which is considered to be closed if and only if A is unsatisfiable. That means if all the branches, suppose if you start with a formula X and you take not X into consideration and all the branches closes, then X is considered to be valid. And how soundness, if if a tableau is closed, then obviously A is considered to be unsatisfiable. And completeness, if a well formed formula A is considered to be unsatisfiable, then any tableau for A is said to be closed. So the idea here is that all the things that we prove it in the case of classical logic, all the properties such as these things can be done by using the semantic tableaux method. A well formed formula A is considered to be satisfiable formula if and only if any tableau for A is considered to be open. And corollary 2 is that a well formed formula A is said to be a valid formula or a tautology if and only if not A. That means you take the negation of the formula, and if it gets closed, then it is considered to be a valid kind of argument. So some of the theorems that we have is that if a statement alpha is tableau provable, that means if you are given a kind of alpha, then you take the negation of that one and it leads to the branch closure, that means it is said to be provable. That means you are saying that X is a tautology, all truths are provable. Then alpha is considered to be a tautology. That means if alpha is tableau provable, that means you take the negation of that one, it leads to contradiction, that means not of alpha is unsatisfiable, that means alpha is valid. So a tableau method is again said to be consistent, and this means that there is no proposition alpha such that you can derive both alpha and even not alphas. So soundness of all this tableau method is considered to be sound, consistent, etc. All the things that you have done in the case of propositional logic by using so many other theorems can be done by using semantic tableaux method. In the same way, you can show that natural deduction method is sound, consistent, etc. Like this, you can say tableau method is also said to be sound, consistent, etc. So soundness of the tableau method, how you do it? It is like this: if alpha is provable in the natural deduction system, it is another kind of system where you prove certain theorems by simply following some kind of valid principles of logic, like modus ponens, modus tollens, etc. Conjunctive, disjunctive syllogism, etc. If something is provable in the natural deduction method in that way, it can very well be done in the case of by using semantic tableaux method also. So that is what it is saying. If alpha is naturally deduction provable, then it also implies that alpha is considered to be a tautology. So anything which is provable has to be true. All the true statements are considered to be provable. So in that sense, propositional logics are considered to be complete. Before going into the details of something, let us consider some examples where how we can use this semantic tableaux method. We will be doing some examples. So let us start with a simple example. That is, suppose if you have some set of formulas like this, just write it here. So now, assuming that if you have some formulas like this, So now you want to check whether P implies R follows from these two formulas or not. So these are set of formulas that we have, which is considered to be gamma. From that, whether P implies R follows or not. So now we want to test whether P implies R is a consequence of these two things. So first thing which you do is you list out all the things, premises first, and then separated by that you have a conclusion like this: P implies R. So now the first step that you do in the case of semantic tableaux method is that you deny the conclusion. So the ideally speaking, the thing is that X is considered to be your conclusion. Now you are denying the conclusion. If the denial of the conclusion leads to contradiction, so when it leads to contradiction, if you deny it and construct a tree diagram, all the branches that occurs in the tree diagram will close. Then it should not be not X, but it should be not of X. So that is nothing but X. So this is semantic tableaux method is dependent on this particular kind of principle. Not X implies a contradiction. BOT stands for contradiction, and that means it should not be not X, but it should be not of X, that is X. So now using the alpha and beta rules, we will be expanding this thing. So while discussing about the semantic tableaux method, we have seen that always use a formula which leads to non-branching rules are the ones which you use it first, and then followed by that the branching rules. So this leads to non-branching kind of thing. It is P and not R. Why? Because not of X implies Y is X and not Y. So now this is checked. You don't have to check it again and again. So that's why we put check mark on this. So now coming back to any other formula. So now if you simplify this thing, it is not P R Q. Why it is not P R Q? The tabular rule for this one, or tree diagram for P implies Q, is not P and Q or Q. So now this is checked. That's why we had put tick mark here. Now Q implies R. Now every time when you apply this tabular rules, you need to see whether a literal and its negation occurs in the branch. So now here you have P here and you have not P here. This branch closes here itself. You don't have to expand it. An inconsistent kind of formula need not have to be extended further. So this closes here. So now this particular kind of information, this is what is left here. This needs to be written under whatever path which is open here, the open branch. So now this is not Q and R. So now if you observe it here, so this branch closes here because of this thing. Q and not R occurs here. So that's why this branch closes, and R and not R occurs here. That's why this branch closes. So that means what we have shown is that denial of the conclusion, that is not of P implies R, leads to the branch closure. So that's why not of P implies R leads to contradiction. So that means it should not be not of P implies R, it should be not of P implies R. Not of P implies R is nothing but P implies R. So you might ask what is the thing that you get from this thing. So the semantic tableaux method is like some kind of decision procedure method. This is a simple transitivity property, P implies Q, Q implies R, and P implies R. This can be proved in this sense, that you deny the conclusion, it leads to contradiction. That means it should not be not of P implies R, it should be P implies R. So this is the way you check the validity of a given formula. Validity in the sense here it is a consequence of this. So you can check validity of formulas like this. I will give you few examples and then I will stop this thing. So suppose if you have a complex formula like this thing. So now we want to prove whether this is a valid formula or not. So when this formula is going to be a valid formula, especially when it is considered to be a tautology. Now we are going to check for the tautology of a given formula. So the first thing that you do is, if assuming that it is X and you take not X into consideration, not of P implies Q implies P, the first thing that you do. So the entire thing is X and this is Y, then it is going to be not of X implies Y, beta rule is this thing X and not Y. Both X and not Y have to be true for making this not of X implies Y true. So in that sense, so P as it is and not of Q implies P is the one which you, this way you list it one after another. So now this again you apply beta rule on this one, it is going to be Q and not P. So now you have P and not P here, this closes. So what did we show? So negation of this given formula leads to contradiction. So that means it should not be not X, but it should be not of X. So that's why it is X. In our case, X is the original formula, P implies Q implies P. So we can play with this formula by putting not P here, then you see that the branch is going to remain open. So for example, if you put not P here, then it is going to be like this, then so this will become P now. So this branch remains open. There is no way in which you can close the branch. So that means a negation of X, that is the one which you started with, doesn't lead to contradiction. So this does not give us guarantee that X is considered to be valid. Some simple other examples that I will be talking about, where you can show a group of sentences are said to be consistent or satisfiable. With this I will start. So let us say you have some sentences like P implies Q, not Q, or something like Q implies R. 1, 2, 3, 4. A little bit complex statement that you take. Let us say you have these 4 sentences. So now we want to show whether these sentences are considered to be consistent or not. So they are said to be consistent only when, after applying the 3 rules, you end up with atomic prepositions. Then ultimately there should be at least one open path. That shows that these are said to be consistent. So consistency is considered to be the most important thing, in a sense that you cannot talk about 2 things like this. It is raining and it is not raining. It is an inconsistent kind of statement. So now again, first strategy that you use is that always use non-branching rules. The one which doesn't lead to branch is the one which you need to take into consideration first. So this is this one. So P implies Q is simplified as PQ. So now this is checked, so that's why you have put a tick mark there. Now any formula that you can take into consideration. So now I am handling this one, not P and not Q. So this is from 3. You can write it justification like this. So now each time when you apply this rule, you need to see whether literal and its negation occurs in any path, open path like this, or branch. So actually this is like upside down kind of tree. All these formulas should be there here, but we have shifted it according to our convenience. So now this closes here because P and not P occurs here, and even Q and not Q, this also closes here. So now there are 2 things, observations that you can make here. Suppose if you did not use these 2 things initially, non-branching rule is not the one which you apply, then what happens is that the proof will become a little bit lengthier. So always it's our strategy. Our strategy is that always apply non-branching rule first, and then so it comes only through our practice. That for example, in the same kind of example, suppose we have not, instead of going into this one, I went to this formula. So then what happens is this. So now the proof will become a little bit lengthy. So now I am opening this formula instead of this. So it is going to be not Q implies R. So Q and not Q, this closes. Now this is checked here. So now coming back to this one, there is no way in which you can close the branch. So now you apply this P implies not Q. So now Q and not Q closes. and P and not P closes. So the idea here is that your proofs can become lengthier if you take if you follow this one first, then followed by that you take this into consideration. So when do you say that a given proof is considered to be an effective proof? An effective proof is the one which ends in finite steps in finite interval of time. So that is considered to be an efficient kind of proof. Unnecessarily there should not be some excessive kind of information. The one which I have showed it in the last thing, that is considered to be an efficient proof because it involves less number of steps. So I will stop here. Then in the next lecture we will be talking about how we can use this semantic tableaux method to solve knights and knaves puzzles. That is the one which we will be taking into consideration in the next class. Welcome back. In this lecture we will be seeing how we can use the semantic tableaux method in solving some of the important puzzles. They are called knights and knaves puzzles, which are constructed by Raymond Smullyan. You will find these puzzles in the book. What is the name of the book? That is the title of the book. In that book you will find all these puzzles. So and the second set of puzzles that we will be dealing with in the next class is lady or tiger kind of puzzles. So using propositional logic, particularly this semantic tableaux method, you will be able to figure out who is knight and who is knave. These puzzles are interesting in a sense that the description of the puzzle goes like this. So there is an island and in that island there are only two kinds of inhabitants. So these two out of these two inhabitants, there are some kind of inhabitants who always speak truths, they are considered to be knights. There are other kinds of inhabitants who always tells lies. That means they always tell false things. For example, if you ask knave, is 2 plus 2 is equal to 4, he will say no. If you ask knight, is 2 plus 2 is equal to 4, he will say yes. So knights tells truths and knaves tell only false things. So it is beautifully, it can be described in terms of two valued logic, where some inhabitants always talk truths and other set of inhabitants talk lies. So now let us consider some problems. So now you went to such a kind of island. Now these are some of the set of problems that you are seeing here. So let us consider the second problem. So that is like this. Suppose if A says I am a knave and B isn't. So you came across A, B. So now A is discussing, A is saying this thing. A says I am a knave but B isn't. So what are A and B? So this puzzle can be described like this. So A is saying I am a knave but B isn't. So this is the only statement that is available to us. So now we need to figure out what are A and B. So now there's some all these puzzles can be solved by means of some kind of representation. So you need to represent these sentences with P, Qs, etc. Suppose if I write simply A, that means A is said to be knight, and if you write not A, that means A is knave. So now there is one more thing which you need to take into consideration here. A is saying this particular kind of statement. So what it means to say A says, let us say X. So how do we represent it in classical logic? So you need to take two things into consideration here. If A says something, let us say he says 2 plus 2 is equal to 4, and that needs to be A says that 2 plus 2 is equal to 4, and the other thing is that if 2 plus 2 is equal to 4 is the case, and that has to be told by told by only A, none other than A. So that makes this thing a biconditional kind of thing. So now it is in that sense we write this particular kind of statement like this. So whenever you have A says something, it is going to be a by implication. Suppose if I say that 2 plus 2 is equal to 4, then A implies 2 plus 2 is equal to 4 is the case, and 2 plus 2 is equal to 4 is implied by this thing that that is said by only A, none other than A. So now how do we represent this sentence, I am a knave? So here A is talking about it, that's why you have to write like this, not A. But is usually translated as and B is not. So B, if you write just B, it means B is knight. Not B means B is knave. But here we have B is not knave. B is not a knave means it is not the case that not B. So that means B has to be a knight. So it has to be like this. So now what we have done here is that we have translated the English language sentence appropriately into the language of propositional logic. So now by using semantic tableaux method, we are trying to figure out what is A and what is B. So now this is like a simple rule which is like this: A if and only if B means either both have to be true or both have to be false. If you understand one example, you can understand all other examples as well. So now this is represented like this, not A and B, and on the other hand we have negation of this and negation of this also, not A and B. So ultimately what we are trying to do here is that under what conditions this formula is going to be satisfiable. When this is going to be satisfiable, especially when you constructed a truth tree diagram, ultimately after exhausting all the tree rules etc., you end up with atomic propositions. That means you end up with atomic propositions, you will not apply the rules. So any in the semantic tableaux method, ultimately the tree diagram ends with atomic propositions. So now this is written like this. So now you see here A and not A, this branch closes, so you cannot go further now in this case. So not of not A and B. So this is using De Morgan's law, you can say like this, not A and not B. Not A is simply A. So now you have A here and not A, this closes. Now the only thing which is left is this one. You have not A and you have not B. So in our original representation, so this is our initial representation. A means A is knight. Not A means A is knave. Means not knight means naval. So in the same way B means B is knight. Not B means B is knave. So the answer that we got is that open branch is the one which you need to inspect. So open branch tells us when this formula is going to be true. So now this is the open branch, not A and not B, not A and not B. So not A means A is a knave and not B means B is a knave. So that's why the answer here is A is knave and B is also considered to be knave. So then only it satisfies this particular kind of formula, or it satisfies a statement that if A says that I am a knave but B isn't a knave, then this is going to be the solution. So let us consider some other interesting problems. For example, in the first problem, what you need to write is that A says all of us are knaves. All of us are knaves can be represented as not A and not B and not C, etc. That tells us that all are knaves. The second statement B is saying that exactly one of us is a knave. I am talking about the first example in this thing. So exactly one of us is a knave means there are three possibilities. Suppose if you take A is a knave, you should ensure that B and C are knights. So this needs to be written like this. I am not going to solve this problem because it takes a lot of board space. So I am just representing this formula, and later you can apply the semantic tableaux rules, and then you will be able to come up with an answer. A says all of us are knaves. All of us are knaves. B is saying what B is saying? B is saying exactly one of us is a knave. Exactly one of us is a knave. So now the first sentence is translated like this: A, if and only if all of us are considered to be knaves. In our representation, if A, B, C are knights, not A, not B and not C are considered to be knaves. So this means not A and not B and not C are considered to be knaves. That means everyone has to be a knave here. That satisfies this thing. All of us are considered to be knaves. If at least one is not a knave, it doesn't satisfy this proposition, that statement that all of us are knaves. Now B needs to be represented like this. This is considered to be a little bit lengthier kind of statement. Exactly one of us is considered to be knaves. So that means it goes like this: if A is a knave, then you need to ensure that other two are not knaves. That means they have to be knights. This is the first proposition. Or that satisfies this particular kind of formula. Exactly one of us is a knave. There are three kinds of possibilities here. Or the other possibility is that A and not B and C. This is one kind of formula, and the other formula is A and B, but C here is a knave. So all these things are separated by this thing. So this entire formula is the one which you need to take into consideration. So now once you apply semantic tableaux rules for this one, then ultimately you need to inspect the open branch, and from the open branch you can study who. You will be able to understand it from the open branch. So in the open branch, for example, if you have A, not B, C, etc., that means A is considered to be a knight, not B means B is a knave, and C means C is considered to be a knight. So let us consider some other examples. I am not solving this problem, but just I am giving you some kind of hint. So let us consider some other interesting kind of problem. Suppose if in the seventh one, for example, A says if I am a knight, then 2 plus 2 is equal to 4. That is a simple straightforward thing, whether A is considered to be knight or knave. If A says this thing, if what is the thing, seventh one, if I am a knight, then 2 plus 2 is equal to 4. If I am knight, then 2 plus 2 is equal to 4. So what can we say about A? Suppose if he is making this particular kind of statement, we need to figure out whether he is a knight or knave. So now usually when we 2 plus 2 is equal to 4 is always true. So that's why we represent it with this letter T. T means those sentences which are always true. They are also considered to be tautologies. So this sentence can be represented like this: A, if and only if this thing, if this sentence is in the form of if P then Q. If this is represented as A and this is represented as B. So if I am a knight, in our original representation it is like this: a knight is represented as A only. This leads to T. This T should not be confused with another prepositional variable. There are two constants that we are talking about, we talked about in the syntax. So they are this thing, T and bot. This stands for tautology, this stands for contradiction. So now we need to find out when this is going to be satisfied. So now it is A, and A implies T, and then not A, not of A implies T. So this is not A and T, and then so this leads to this one, A and not of T. So suppose if you have 2 plus 2 is equal to 4, then the negation of that one is going to be contradiction. So this not of T is equivalent to ulta t, that is pod. So, that means there is a contradiction here, this branch closes here. And now coming back to these things. So, you have A here and you have not A here, this branch also closes. So, now the only branch here is this thing. We have this particular kind of solution where if A says if I am a knight then 2 plus 2 is equal to 4, the solution that we are getting here is that from the open branch you can find out what is what. So, A and T is the one which we have, A and T here. So, that means A has to be true, I mean he has to tell the truth, because A and T is going to be true only when both are considered to be true. So, this is already true, it cannot be naive, because if it is a naive the sentence is going to be false. So, that is the reason why we can say that A is said to be knight. So, like this we solve these puzzles. Now, let us enter into the 10th problem, which is a little bit interesting. So, there are two individuals X and Y who are being tried for participation in a robbery. They are considered to be the witnesses. So, now no, they are the guilty or innocent, we do not know. So, now we have these inhabitants, so like A and B, they are considered to be, now it so happened that they turn out to be the witnesses of X and Y. So, they have to report to the judge or lawyer, whatever it is, and each of A and B again is considered to be either knight or knave. So, now the witnesses make the following statements. This A and B, they can be either knight or it can be even knave, but these A and B make these statements. From this we need to figure out whether X is guilty or Y is guilty, etc. So, now the first statement is like this. A says if X is guilty, so is Y. So, this problem can be solved like this. So, first you need to represent it appropriately into the language of this thing. Again you take this representation into consideration. A stands for A is a knight, not A means A is a knave, B means B is a knight, etc. So, now so the first statement says that A is saying that if X is guilty then Y is. This can be represented as this thing. If X is guilty implies Y is also guilty. So, that is the first statement, and the second statement is this thing, either X is innocent or Y is guilty. So, before that you need to have some more representations like this. Suppose if you write X is guilty, then obviously the negation of that one is considered to be X is innocent. In the same way, suppose Y, just if you write Y, Y is guilty, not Y means Y is innocent. So, you can take you can consider another kind of notation. Suppose if not X is considered to be guilty for you, I mean the one which you represent it as guilty, then obviously X is considered to be, if not X is guilty, then X is considered to be innocent. Opposite of that one is considered to be innocent. Now, the second statement is like this, either X is innocent or Y is guilty. X is innocent, X is innocent is this one, not X in our case, in our representation, or Y is guilty means 1. So, this is the one that they are trying to make. So, this statement is made by B. So, that is why you write it like this. So, now the first statement A is telling about this thing, that if X is guilty, Y is also guilty, this is the one, so as Y, that means this can be translated as simply if P then Q. And the second one, B if and only if either X is guilty, X is innocent or Y is guilty is translated in this sense. So, now forget about the problem here. Now, we manage this thing with the help of the formulas that we have. So, now applying the 3 rules for this one, we are trying to figure out who is guilty and who is innocent. So, So first I will apply on this one. It is either x implies y or not a, not of x implies y. So now this is expanded to this one, x implies y means not x y, and here it is x and not y. So you check this formula, and that is why you tick mark this one. So the second formula is the one which we have. Ultimately what we are trying to do is that we are trying to see when these two statements are considered to be consistent or satisfiable, under what conditions these two are true. So we have two things like either b not x or y, other one is this thing, not b not of not x or y. So it is x implies y means x if and only if y means either both are true or both are false, not b is the case, and not of x or y. Just expand it, then you need to note that from at least if you have one open branch, that gives us a solution for this one. So this is further expanded, it can be expanded to this thing, not x or y is written in this sense. So now this is one path and this is another path. So now we need to see whether a literal and its negation occurs in any one of these branches. So a x implies y not x, b not x. So this appears to be an open branch. In the same way b not x a, it is not closing, this itself is considered to be an open branch. So we can construct the whole tree to find out other solutions as well, but one open branch will tell us when this is going to be true. So now from the open branch you construct the answers for this one like this. So the situation here is like this, a not x, b not x. This is one thing. That means it tells us that if a and b are considered to be knights, then x has to be guilty here. That is the one that we are getting it. The other solution is this one. This is not of not x is x, and not of y is this one, not y. So here you have x and not x, this closes here, so you do not have to go further. So now here we have another solution where you have a not x, b y, a not x, b and y. So from these two things we can make out whether what is considered to be who is considered to be guilty and who is considered to be innocent. So now we have two solutions like this which satisfies this particular kind of formula. So from this definitely you can say that not x means x is innocent. Now this is the same thing which we got it here in the second thing also. That means x not x here means x is innocent, and y in our representation y means y stands for y is guilty. So now from this you can make out from the open branch, you can see the solution here. So now the answer for this one is that you can expand the other branch like this. You have to apply the same trigonometric tableau rules to get to know the other things, but one open branch will serve our purpose, you do not have to open the entire thing. So our solution is not x, I am putting it in the this thing, and then y. That means if a says x is guilty so as y, and b says that either x is innocent or y is guilty are the sentences that are given to us, then obviously not x y should be the case. That means x has to be innocent and y is considered to be guilty. So like this we solve all these problems. You need to note that these problems can also be solved in a slightly different way. What you need to do in that particular kind of thing, particularly in the book, Raymond Smullyan's book, how we solve these problems is that first you assume something and your assumption leads to some kind of contradiction. That means your assumption is wrong. First of all you start with A is a knight, then it leads to contradiction. That means A should not be a knight, he has to be a knave. So there are varieties of ways in which you can solve these problems, but we are highlighting particularly on the semantic tableaux method. So these problems are obviously very interesting. If you understand how the first and foremost thing you need to note is that in all these problems, first you need to represent it. Once you represent these formulas, then you look for the satisfiability. It leads to some satisfiability problem. Under what conditions the given formulas are said to be true. I mean when it is said to be satisfiable. So now in the process of finding out the satisfiability of a given formula, you will come up with this that from the open broth you will come to know your answers. So I will stop here. In the next class I will be talking about some examples, very interesting examples with respect to lady or tiger. These problems are also very interesting, and then we will see how we solve those puzzles. And another interesting important thing you need to note is that these puzzles can also be solved by using truth table method. So all methods can be used, but semantic tableaux method seems to be a little bit easy to use, particularly when the number of propositional variables are less. So these knights and knaves puzzles, you need to note that it looks very easy for us, especially when A always tell truths, B always tell lies, etc. But what happens when you introduce another inhibitant who depending upon his will or wish, sometimes he tells truths, sometimes he tells lies, depending upon his vested interest. So if you introduce pi into that particular kind of inhibitants, then these problems will become a little bit complex, and then it's fun solving these puzzles. I will stop here. Thank you.